Spherical coordinates are slightly different from cylindrical coordinates. Spherical coordinates still measure where we are in terms of three quantities, but now these have new names. They're all Greek letters. This first one looks like kind of like a letter P. That's the Greek letter rho, or the lowercase letter rho from the Greek alphabet. Theta is a thing that we're familiar with because we see it to measure angles all the time. The last one is a Greek letter called phi. And each of these measures a physical quantity. Rho, the first of these, is a measure of distance from the origin. So rho is always supposed to be non-negative. It tells us how far away inside three-dimensional space we are from the origin, 0, 0, 0. Theta is a longitude coordinate. So theta is going to tell us, if we're thinking about spherical coordinates as kind of like coordinates on Earth, the theta coordinate is going to tell us what exact vertical longitude line we lie along. And phi is more like a latitude coordinate. It's going to tell us what kind of circular latitude line we lie along as well. Theta is going to be measured between 0 and 2 pi, or minus pi and pi, or something like that, you'll sometimes see. Phi is going to be measured between 0 and pi, and we'll talk a little bit about the coordinate phi. Here are the formulas for spherical coordinates, and there's no kind of shortcut to this. The formulas for spherical coordinates take a little bit of work to write down or remember. X is rho cos theta sine phi, y is rho sine theta sine phi, and z is rho cos phi. Physically, let's draw a little bit about what these say. So in terms of our rho coordinate tells us distance from the origin. So if I write down rho is equal to 1, the physical shape that I'm going to get is a sphere centered at the origin, radius 1. If I set rho is equal to 2, I get a sphere centered at the origin of radius 2. As rho gets bigger and bigger and bigger, I'm going to slice out progressively bigger and bigger spheres, but the radius increases uniformly. So that's what the rho coordinate does, is it kind of tells us what radius of sphere we're on. The theta coordinate is actually exactly like it is in cylindrical coordinates. The theta coordinate tells us, at theta is equal to 0, we're living over top of the x-axis. And then as theta grows, we slowly start to swing out towards the y-axis. We reach the y-axis at theta is equal to pi over 2. So what theta does is it measures kind of an angle that we make with the x-axis. So when theta is equal to 0, we're this vertical plane. When theta is equal to pi over 2 or pi over 4, we make a 45-degree angle with the xy plane. When theta is equal to pi over 2, we're over top of the y-axis. And as theta continues to grow, this angle that we make with the x-axis and the y-axis starts to progressively grow as well. So that's what the theta coordinate tells us. But it's kind of helpful to, instead of drawing it that way, to imagine, say, we've already fixed rho and we're thinking about our position on the Earth. In those terms, we could think of theta is equal to 0 as being this longitude line that goes from the North Pole to the South Pole and cuts out all those points along a particular longitude that points in the same direction as the x-axis. And then theta is equal to pi over 4 gives us this longitude line. Theta is equal to pi over 2 gives us this longitude line, and so on. So all of these longitude lines are very naturally expressed in terms of theta coordinates. And so spherical coordinates, for this reason, are kind of handy for measuring positions like on the Earth. The coordinate phi is very much like a latitude coordinate. We're out of space here, so let's go to the next slide. The latitude coordinate is different from the way we usually measure latitude on Earth. So latitude on Earth is usually measured with 0 degrees at the equator, and 90 degrees north or 90 degrees south tell us about the north and south poles. But in spherical coordinates, it's slightly different. Instead, we have 0 degrees living at the North Pole, we have 90 degrees living at the equator, and we have 180 degrees living at the South Pole. And as we go progressively around the Earth, we sweep out different angles. And so one interpretation of phi is that it's an angle that we make. I'm sorry, I just drew a theta while I was talking. One interpretation of phi is that it's an angle that we make with the North Pole if we draw a line from the center of the sphere up to ourself. So here is what happens then when I have different values of phi. So when phi is equal to 0, I'm definitely at the vertical axis. I'm definitely at the z-axis. When phi is equal to 45 degrees, which is the same thing as pi over 4, I'm looking at all those positions that make an angle of 45 degrees with that line, and those actually form a cone. It's the cone consisting of all those points where they make a 45-degree angle. When phi reaches pi over 2, I'm getting all those points that are on the equator. So that's the horizontal xy plane. And then phi is going to kind of create a sequence of cones that goes downwards until it reaches the South Pole. And in terms of what we did with theta, we can also draw these on the surface of the Earth instead. We could say, hey, when we have phi equals 0, we're definitely at the North Pole. When we have phi is equal to pi over 4, 45 degrees, we're definitely on this particular circle. When phi is equal to pi over 2, we're definitely on this circle. Then we reach 3 pi over 4, and then we reach phi is equal to pi, and that's definitely at the South Pole. So that's what the angle coordinate phi does.